Let's talk about the Fabric data plane. The short answer for what the data plane is in the Fabric is the VXLAN protocol. With the VXLAN protocol, we are going to be able to move traffic within our Fabric. And this particular protocol will be able to encapsulate Ethernet frames within IP packets. So I will need devices that will be able to encapsulate Ethernet frames inside IP packets and devices that will be able to de-encapsulate these Ethernet frames that are included within IP packets. These are known as VTEPs or VXLAN tunnel endpoints, and within my Fabric, my VTEPs will be my edge nodes, my border nodes, and to some extent the Fabric mode access points, because they will be creating VXLAN tunnels to the edge nodes they are connected to. That will be the short answer. If you want a longer answer with more details, keep viewing this session, because we're going to talk about first why we need a data plane, and secondly, what are the modifications that Cisco made to the standard VXLAN. First of all, why do we need this data plane at all? Remember that we have a layer 3 pure underlay, but we are going to connect that underlay to traditional devices that are operating in a traditional way. They are going to be based heavily on broadcast, for instance, ARP request, and they are going to still use DHCP request, and they are used to work within the broadcast domains. So we need a way to accommodate that traditional layer 2 based operation with our new layer 3 pure IP based underlay. So by doing so, we will need to avoid extending the end devices broadcast domains into our enterprise network, as we did with traditional networks. Remember that in traditional networks, we will have to set up VLANs here within our enterprise network in order to transport traffic that belongs to end users. We don't want to do that, because we want to maintain our underlay as a pure layer 3 network, and at the same time we need to let our users move. So for instance, if a user is first connected here and then it is connected here, we need to let this user keep its IP address and broadcast domain. The same applies for wireless users. We need to let them roam across our enterprise network and let them use the same IP address and broadcast domain as they move across the network. So in order to do so, we know that my underlay alone cannot do that. So we need a tunneling protocol that will help me be able to move traditional layer 2 frames within my pure IP underlay. And that is where the overlay kicks in. So I need a protocol that will help me do that. If you think about it, carriers have been doing something similar. They have IP and MPLS networks running for years, and they are able to let their clients move layer 2 traffic between distant endpoints by using the carrier MPLS networks. In order to do that, the carrier has been using several types of Ethernet over MPLS technologies, such as L2 VPNs, pseudo wires, and so on. But we cannot do that because we don't have MPLS in our enterprise network. There are other encapsulating protocols such as GRE or IPsec, but we cannot use that because they are IP over IP encapsulating protocols. So the answer for my overlay will be to use VXLAN. VXLAN means a virtual extensible LAN. It will let me encapsulate frames. It is a standard. It is based on a publicly available RFC. It is a standard that was created or invented for the data center and for cloud environments where engineers needed a protocol that let them move their wireless machine across their network seamlessly. So we're going to leverage that for the fabric. So the way it works is this. An Ethernet frames enter our fabric. Let's think that it is an AO2.3 Ethernet frame, and we are going to encapsulate it within an IP packet. Remember that we need to set up an IP header. So in order to set up an IP header, we need a source IP address and we need a destination IP address. So if we are sending this packet between these H nodes, this source IP address will be the loopback IP address that belongs to this BTEP that is encapsulating this frame. In other words, it will be the loopback IP address that belongs to the H node that is transmitting this packet. And the destination IP address will be the loopback IP address that belongs to the BTEP that is going to receive this packet. In other words, it will be the H node, the loopback IP address that belongs to the S node that is receiving this packet. So with this information, the packet is able to move from here, H node, to this H node, to this other H node. Once this packet arrives, we need to let this H node know that it is receiving a VXLAN packet. And in order to do so, we are going to use UDP. We are going to set the destination port for UDP to the value of 4789. So when this H node receives this packet, it will examine the UDP header and it will notice the destination port is 4789. At that moment, it will notice that it will have to work with VXLAN. So it will have to de-encapsulate this frame, but it will have to read what is within the VXLAN header before doing so. Because we are going to carry extra information here in the VXLAN header to let this H node know how to process this frame. Eventually, if everything works right, the encapsulation will work and this Ethernet frame will be delivered to the destination device. This is how the standard VXLAN works, but Cisco modified it in order to carry more information. So it created a new standard, a new proposed standard, an extension that is known as GPO, because it is the VXLAN group policy RFC. So that is what is GPO. Before going into details about GPO, let's make a parenthesis here and talk about host pools and Anycast gateways. Remember that in traditional networks, you will use VLAN, for instance, VLAN 10, and you will correlate this VLAN with a prefix, let's say 10.1.1.0/24. So all devices that lives in this VLAN or in this broadcast domain will use an IP address with this prefix 10.1.1. whatever. And you will choose one device that will hold the default gateway IP address. For instance, you will choose one device that will be using the IP address 10.1.1.1 will be the default gateway for this VLAN. So we have something similar in SD access. You can think of something similar. There are several similarities between this construct and what we know as host pools. So let's define this host pool A, where we are going to use the subnet 10.1.1.0/24. So in this case, what we're going to set up in our fabric is we are going to choose all the edge nodes that are going to serve this host pool A with the same IP address. We're going to create switched virtual interfaces at each edge node, and we are going to assign these SBIs the same IP address, the same IP address, the same IP address, and then we are going to also use the same MAC address. This is what is known as Anycast gateways. So after explaining what is a host pool and an Anycast gateway, we're going to go with what Cisco changed in VXLAN. First of all, from the first flags field from the original VXLAN header, Cisco took three of those reserve bits, formerly reserve bits, and provided with a new meaning. So from the 16 original reserve bits, Cisco took 3 of them so they can control the way that we are going to apply tags and whether or not the VTEP will learn the MAC address that is inside this Ethernet frame. From the following 16 bits reserved space, Cisco took it and created the group policy ID field. So given we have 16 bits for this new field that Cisco created with GPO, we can store scalable group tags. And given they are 16 bits, we have a possibility to have around 64,000 different scalable group tags. Notice that it is important to carry scalable group tags because every single frame that enters our network will get assigned an scalable group tag. And this scalable group tag will travel through the VXLAN tunnel, particularly in this new field that Cisco created, which is a 16-bit field known as the group policy ID. Remember that scalable group tags are important because they are the basis of security for the fabric. Let's call this scalable group tag that this gets assigned here the source scalable group tag, just for a matter of explanation here. And when this frame wants to exit the fabric, this point of exit has also related an scalable group tag that we will call, for just a matter of explanation, the destination scalable group tag. So we have a source scalable group tag and a destination scalable group tag. And at this moment in time, when this frame wants to exit, we can apply an scalable group access control list. This is a way that we ensure and enforce security within the fabric. So notice the importance of the scalable group tags. Remember, scalable group tags are assigned when the frames enter, and they are carried over this frame, this field that Cisco is proposing with GPO, that is known as group policy ID. The next field within the VXLAN header is the 24-bit BNI. So it is a 24-bit wide. Just make a note here that this value matches with a Lisp instance ID. We are not talking about Lisp here. We are going to talk about more detail about Lisp in the control plane session. Just notice that this value must match with a value within the configuration in Lisp. And this value will have two natures in the fabric. It can be either be a layer 3 VNID, or it can be a layer 2 VNID. Remember that layer 3 VNIDs work like BRFs, and layer 2 VNIDs are something similar to VLANs. So next we are going to explain when we are going to use layer 2 VNIDs within the fabric and when we are going to use layer 2 VNIDs within the fabric. Notice that there is still another 8 bits that are reserved within the header, and these are not used. So we were talking about this. And let's examine when we are going to use layer 2 VNIDs. Layer 2 VNIDs identify or maps VLAN numbers. So if you in a traditional network had a VLAN number of 10, for instance, you can map it to a layer VNID of 8020. Remember that layer 2 VNIDs starts with an 8. And we are going to use that, for instance, when transporting traffic inside a host pool. So imagine that you have a device here that has the IP address 10.1.1.1. And you want to communicate that device with this other that has the IP address 10.1.1.2. They are clearly in the same host pool. So when communicating devices in the same host pool, we are going to create a tunnel. And when constructing this tunnel, this VNID value will be set up to a layer 2 VNI, because we are communicating devices inside the same host pool using traditional forwarding. So this value could be, for instance, 810. Now let's see an example in which we will use a layer 3 VNI. So imagine that this device has the IP address 10.1.1.1, and this device has the IP address 10.2.2.1. This device belongs to host pool B, and this device belongs to host pool A. So in this case, given we are communicating devices between different host pools, we are going to use a layer 3 VNI. Let's say 4001. Remember that VNIs are identified by the number 4. In order for this to happen, these host pools, host pool A and host pool B, should live in the same layer 3 VNI 4001. So there are other scenarios that we will have to look into in order to know when to use layer 2 VNIs and when to use layer 3 VNIs. For instance, if you're moving traffic inside the same pools using traditional forwarding, you will use layer 2 VNI. But if you were transporting traffic inside the same pool using enhanced forwarding, you will use layer 3 VNI. So this can get a little bit more complex, and we will talk about that in another session.